Hello everyone and welcome you all to the 28th lecture of this NPTEL course where we are discussing the magnificent standard model of particle physics. And in the last lecture, we have started doing this calculation for cross sections for a QED process, which you all know, like E plus E minus going to mu plus mu minus or tau plus tau minus. And we are now using a new technique which is called the Helicity amplitude technique. And in this technique, what we are doing, that we are basically trying to write all the explicit form of the spinors, and we are writing them in the left-handed and right-handed combinations or up or down configurations that is possible. The only thing that we have done is to kind of identify that the z-axis of this collision is along the direction in which the electron is appearing, and E plus is actually coming in the minus z direction in the center of mass frame. So uske baad using that we are identifying the U up, or what you call the UR, the particle spinors, and the particle right-handed spinors, particle left-handed spinors, the antiparticle right-handed spinors, antiparticle left-handed spinors, right? And so therefore we have all the configurations of electron, positron, tau minus and tau plus. So the important point here is to remember that for electron configuration we are using theta equal to 0 and phi equal to 0. For positron, theta equal to pi and phi equal to pi. The tau configuration is like that, that theta is theta because tau is emerging at an angle theta if you look into this diagram, and tau plus is coming out in the opposite direction, so it is pi minus theta and phi is equal to pi. Okay. So with that we have written all the spinors explicitly using the helicity eigenstates that we derived in the class. Okay. So now the next target will be to write the different current configurations, and you remember that the amplitude for this E plus E minus going to mu plus mu minus is basically a product of the electron current and a tau current. So this was the electron current and this was the tau current. So you have a form like V bar gamma mu U and U bar gamma mu V. So this is for the tau and this is for the electron. So we first wanted to write explicitly the tau current and using the different helicity combinations that it can get contribution from, and we saw that there are only non-zero configurations or non-zero combinations of currents coming from the combinations of RL or LR. That means when the tau is right-handed and the tau plus is left-handed, and when tau minus is left-handed and tau plus is right-handed. So these are the only non-zero contributions that we actually got, whereas the RR and LL combinations are identically 0. Now it's time that we construct the electron current part of this matrix element, right? And the electron current part, if you remember, is actually of the form of V bar P2 gamma mu UP1. So this is exactly what we wrote. This is V bar P2 gamma mu UP1. Now this particular form of the current, electron current, you can also say that this is nothing but U bar P1 gamma mu Vp2 dagger, right? So this is explicitly what we did calculate in a couple of lectures back, that this is when you take the dagger of U bar P1 gamma mu Vp2, you actually get V bar P2 gamma mu Up1. Now U bar P1 gamma mu Vp2, this is exactly the form of the tau current, correct? So the tau current that we found out, so this is exactly the form. You see that this is U bar gamma mu Vp4. So if you take the dagger of it, I am actually going to get the form of the electron current. The only difference that is the momenta that are sitting here, the momenta that are sitting here, but that is something that I am going to address in a moment. But for the time being, what I just see that if I just take a dagger, I am going to get that particular form. Alright, so therefore what is the demand? The demand is as follows, that without doing any calculation at all, we can conclude that the Hermitian conjugate of the tau current which we have calculated will be giving me the electron current, however with a proper choice, and that choice is that in this particular case I have to resort to theta equal to 0. correct. So let's look into the RL configuration. RL configuration का मतलब क्या है? Now I mean that the electron is essentially right handed, that means I have U up P1, right, and positron is left handed, that means it will be represented by V bar down P2, right. So therefore what I am looking for is actually V bar P2 gamma mu U up P1, but let's actually take it from the tau current. So therefore I say that this is V bar P4. Let's find out V bar P4 gamma mu U up P3. That will be nothing but U bar up P3 gamma mu V down P4 star. Yeah. So I have to take complex conjugate element wise, and I am going to get this combination of V bar P4 gamma mu U up P3. And so therefore what it will be? So let's look into this thing. The RL current was 2E 0 minus cos theta I sin theta. So the only change that I am going to have is here in the I, that is going to become minus I, and everything else is going to remain the same. So this is exactly the same. And also you remember that in this particular case, this P3 and P4, the magnitudes are not different. The magnitude is essentially the same as E. So this very well provides me with the, you can say that this very well does the job for V bar down P2 gamma mu U up P1. So this does the job very much for this particular one. Similarly, I can now look for the LR combination, where I basically say that the electron is now left handed. So I have to look for U down P1, and E plus is right handed, where I have to use E V bar up. Okay. So with this one, therefore I can say that V bar up P4 gamma mu U down P3, this is the electron LR combination, which is obtained from the tau current by just taking a complex conjugate component wise. And if I just look into this expression, this is 2E 0 minus cos theta minus I sin theta. So I just have to change this minus I to plus I, and then I am done. So this is what I have done. So I have the expression for this JE LR combination. So however, I have to also remind myself that for this case the electron and positrons are not coming at an angle theta, but I have to choose theta equal to 0 for the electron current, and so therefore what I have is for JELR, I am just going to put theta equal to 0 in this cases, and so therefore I have JELR is equal to 2E into 0 minus 1 I 0, and JERL is equal to 0 minus I 1 minus I 0. Okay. And once again LL and RR combinations are identically 0. So therefore, what are the non-zero contributions that we are actually having? This is very interesting. We have RL to RL, that means you have the electron and positron, when one is right handed, one is left handed, it produces a RL combination, that is non-zero. RL to LR, that is a non-zero combination. LR to RL, that is a non-zero combination, and LR to LR. These are the non-zero combinations which are actually possible, because RR and LL combinations are identically 0. So those are not contributing, right? So let's try to draw these helicity combinations pictorially, and there will be something interesting for you to look into. So for example, RL to RL, iska matlab kya hai? So your electron is right handed, that means your spin projection and the momentum direction are aligned. Your positron, that is actually left handed, that means your momentum and spin projections are opposite, right? So this is the spin projection by this broad arrow, so to say. So this is the spin projection for you, and this arrow is the momentum projection for you. Now this must not be confused with the notations that we have used in the Feynman graphs. Feynman graphs का जो momentum notation है वो मैंने कुछ अलग लिखा है, so I have written it differently, but when I am writing this helicity combinations I have used this momentum arrow and spin arrow with a different notation. Okay, so this must not be confused with the Feynman graphs which we actually did. But you are, if you do not like this notation, you can, because I just wanted to show the spin projection on top of the momentum direction, so I did it like this. Okay, so this is RL configuration, and similarly the RL configuration for the final state mu minus and mu plus which are being produced. So this is mu plus, for which this is left-handed. So the spin and the momenta are in opposite direction. So this is the RL to RL. Similarly, you have RL to LR, right? So the initial state electron positron configurations remains the same, but for muon and anti-muon the spin projections are being flipped. Okay, and then you have LR to RL, LR to RL, and here also you see that the spin projections you can draw, assuming that the electron is left-handed, positron is right-handed, muon is right-handed, anti-muon or anti-tau. I mean you can draw it for, I am just showing it for mu minus mu plus, but this is equivalent to tau minus tau plus. So let us draw one of these graphs to see how well we understand actually this kind of graphs. So the initial configuration for electron left-handed I have already drawn. So this momentum arrow and the spin arrows are opposite, and for the positron also the momentum arrow, for the positron because it is right-handed, the momentum arrow and the spin arrows are actually aligned. For the muon, mu minus, it is actually left-handed. So basically the spin will be projected opposite to the direction of the momentum, and the mu plus, this is right-handed, so it will be spin projecting along the motion of the anti-muon. So here you actually see that the spins are always aligned. The initial state spins, these are like going towards this direction, so this is like this direction, and this one is like going this direction, right? Here this is this one, the initial spin, and then this is going in this direction, right? Here this spin is going along this direction, and this is actually going along this direction, right? Here also your initial state spin is aligned this direction, and the final state spin is aligned this direction. So it's spin half objects, right? And the eigenstates are plus half and minus half, and what you are trying to say that the spin 0 combinations are not contributing. It is only the spin 1 states which are actually eventually contributing, either it is spin 1 or minus 1. 1 or minus 1, both in the initial and the final state, but with an angle. I am going to come back to this discussion a little later, but let us carry on the computations, because we have now identified all the currents, so to say, for the electron and tau, and so, or electron or muon. So now I am in a position to calculate all the products essentially. So let us calculate m of LR going to RL. तो ये combination पहले लेते हैं. So this is basically the multiplication of these currents that we have already explicitly find out. So LR to RL, you take the J mu LR combination and J mu tau RL configuration from your expressions that you actually have made. So you do the matrix multiplication, and it turns out to be E square into 1 minus cos of theta. You do m LR to LR, and you take the LR combination and for the electron current and LR combination of the tau current, and you do the matrix multiplication. It turns out to be minus E square into 1 plus cos theta. You do m RL to LR, and once again you take the individual currents, multiply them, and find that this is coming out to be E square into 1 minus cos theta, which is the same as LR going to RL. And similarly for RL going to RL, you find that this is coming out to be minus E square into 1 plus cos theta, which is m of LR going to LR. Now, this is amazing, right? So, therefore, now we are in a position to write the matrix element square. So, I have dropped. So, this is 1 by 4 of all the combinations, out of which the RR and LL combinations are 0. So, the non-zero contributions only coming from m RL square and m LR square, out of which m RL square only have m RL going to RL and m RL going to LR, and similarly m LR is going to only have LR to LR and LR to RL combination, and if I add everything, I get that same nice expression of the matrix element square which we found out in the trace technology. So, if you remember, the matrix element square using the Mandelstam variables was actually coming out of the form of 2 e to the power 4 by a square into u square plus t square, and once you use u equal to minus 2 e square into 1 plus cos theta and t is equal to minus 2 e square into 1 minus cos theta, the matrix element square was essentially this e to the power 4 into 1 plus cos square theta. So, this is absolutely fully in agreement with the calculation that we did previously. So, this trivially once again to recapitulate that it is going to give you a d sigma d omega differential cross section that you can write, and that is going to give you, this is 1 by 64 pi square s p f star by p s p I star in the center of mass frame with the matrix element square, and once you choose the matrix element square as you have derived already, so you get the differential cross section of the form of alpha square by 4s into 1 plus cos square theta. This alpha is what is called the fine structure constant. It is e square by 4 pi, and the value is usually 1 by 137, right? Now, this is something which is going to predict, as I told you in the last class, that a symmetric distribution in terms of cos of theta. But however, there is one part which I would like to mention now, that an experiment in 1985 which probed this behavior of e plus e minus to mu plus mu minus, they actually saw something not quite in agreement with what we have obtained. They rather have seen that there is a bit of asymmetry, backward asymmetry in this distribution, which we couldn't actually see from this calculation that we have done in both the matrix element square process and in the Helicity amplitude technique. So, therefore, this raises the question, if the calculation that we are doing is perfectly all right, the QED is fine, or the question is if there is something more. The answer is yes, there is weak interactions which will also contribute and make this cross section forward backward asymmetry. I am going to repeat this calculation after we actually define what is weak interaction and so on. So, we are going to come back to this calculation once more and find out exactly the one that is actually seen in the experiment. But on the other hand, if you can find the total cross section, so just because this is 1 plus cos square theta, d cos theta integration is trivial, phi dependence is not there, so d phi becomes 2 pi, and you simply see 1 by this cross section is turning out to be 4 pi alpha square by 3s, and this cross section is in good agreement with the theory up to a center of mass energy of 40 GeV, and so this sigma s, if you plot with respect to the square root of s, this shows this kind of a falling behavior, and this can be very nicely explained up to 40 GeV, and which tells that the QED is actually doing good excepting for that asymmetry part, and there is something which happens around 50-60 GeVs, and or rather around 80 GeVs, which has to take into account something more, which is nothing but the weak interaction. I am just going to end the class by telling you a little more of what we were discussing regarding this, the spin configurations. You see that, out of the different combinations which are possible, like this RL, that we had, RR that we had, LR that we have, and LL that we have, the only non-zero configurations which are possible are essentially LR and RL, correct? So, these are the only non-zero amplitudes for the current which is possible for the initial state and also for the final state. So therefore, what we actually see that the only non-zero combinations which actually come is from the RL to RL. Now RL to RL, and of course RL to LR is also possible, but if you remember that your current of LR to RL and RL to LR, these are identical, and similarly RL to RL is actually identical to LR to LR. So the two independent combinations which are possible is RL to RL and you can say LR to RL, right. So this basically means what, that if you look into the spin configuration of this, once again, so this is the momenta and this is the spin, and so you can say that the spin is like, you know, for this configuration this is spin is actually along the z axis. So you can say that this is the combination which is like 1, 1 z. इसका मतलब क्या है मैं एक मिनट में बताता हूँ. And similarly for this configuration like mu plus mu minus that you produce, the spin configuration is something like 1, 1 theta, and for this combination is essentially for LR to RL. Once again, you know, you can draw your LR to RL very easily, and it's basically saying that the spin is actually going along the negative z direction. So you have something like this, and you can say that this is 1 minus 1 z, and this combination is 1, 1 theta, right. So what we are saying? We are basically saying that in this particular annihilation process, the spins of electron, positron, tau plus and tau minus, they are aligned. They are aligned means they do not annihilate. The combinations which annihilate, this contributes absolutely to 0. So the eventually what we happen, that the non-zero amplitude only occurs when the spins combine to give you spin configurations of plus minus 1. So you can imagine that you have spin plus half and plus half. So this can give you plus 1. You can have plus half minus half, this can give you 0. Once again you can have minus half and minus half, that can give you minus 1, and it turns out that the only configurations which are going to give you non-zero contributions to the amplitude is when these are plus 1 or minus 1. So basically to say, for example, RL state, this is something like you can represent by a kate S comma Sz. So the total spin of this system is actually 1, and the Sz is actually aligned toward the positive z axis. On the other hand, what is LR combination? LR combination is this one where the spin is combining to 1 and the spin is combining or pointing towards negative z axis. So this is Sz is equal to minus 1. So therefore these are the two spin configurations which are contributing to initial state electron positron beams or electron positron currents. Now I also have to evaluate somehow the tau currents, and that also I have seen from these graphs that we drew earlier, that it is eventually either pointing along this direction or pointing down, either to plus theta or to pi minus theta, right. So it's also a spin 1 combination, but now it is subtending an angle theta with respect to the z axis. Now the question that we would like to ask, that is there any possibility that I can somehow express this 1, 1 theta which this tau plus tau minus configuration is producing with respect to the, or with respect to the basis vectors or basis states like 1 plus 1, 1 minus 1, or you know what you can call 1 0. Can I do that? So the point is you can do that by computing the following: the operator corresponding to the composition of the spin along an axis defined by an unit vector n at an angle theta to the z axis can be defined by Sn, which is half n dot sigma. And using this, what we can do, that we can express the spin states of the tau plus tau minus system in terms of the eigenstates of Sz. What does it mean? Say for example, I am not deriving this, but you should try derive this at home, and what you should find out that this 1 comma 1 theta, this is eventually an RL configuration in the tau plus tau minus 1, right. This can be expressed in terms of the 1 minus 1 state with a factor of half into 1 minus cos theta. This you can say that the LR combination. It can be expressed in terms of 1 0 with a prefactor of 1 by root 2 sin theta, and it has a prefactor of half into 1 plus cos theta with respect to the 1 plus 1 basis, and this is the RL configuration that we actually talked about. So, this 1 at theta, this can be expressed in terms of the combination of 1 minus 1 and 1 0 along the z axis, so to say. Okay. And this will basically now allow you to see that if you take M RL going to RL, then basically what you are going to evaluate, you are basically going to take the inner product of 1 plus 1 state with 1 plus 1 theta, correct. And if you do that, you can clearly see that this will basically see this particular coefficient, which is half into 1 minus cos theta. And similarly, if you want to find M LR to RL, that basically means that you have to take a projection of 1 minus 1 to 1 plus 1 theta, and then you can clearly see from this expression that this is nothing but half into 1 minus cos theta, and these are exactly the expressions that we actually found out with this helicity amplitude technique. You see, this is exactly the amplitude 1 minus cos theta and 1 plus cos theta. So, therefore, you can say that these non-zero amplitudes that you actually find out in this E plus E minus tau minus production are nothing but the spin configurations which are contributing those to those final states. And this is a nice visionary that you can actually build. So, therefore, with this we would like to conclude this lecture today, and we are going to discuss a little more of QED, but in some other contexts, and then we will take up the weak interactions next. Thank you for your attention, and I am going to see you in the next lecture. Thank you.